One of the abundant waste products in wood industry in Estonia is lignocellulose. Our next speaker will raise the curtain on how lignocellulose could be used as a sustainable platform for production of novel materials. Please welcome Associate Professor from the University of Tartu, Siim Salmar.
Hello, everybody. First, thank you for Kaspar to invite me to present a talk here. It's very nice to be third. If I'm going to talk about a little bit lignin, and Timo has presented already the main part of it. Okay. In my talk, like I said, I'm focusing a bit lignin, or even hydrolysis lignin, and will introduce some new technologies what we're using to valorize lignocellulosic biomass. Okay. This part is done already. As you all know, lignocellulosic biomass as well as wood consists cellulose and hemicellulose and lignin. And like Timo mentioned already, all currently used industrial applications and technologies prioritizing only cellulose or cellulose and hemicellulose, the sugars. And lignin is actually most of it all burned to produce cheap energy and also recycle the chemicals. Not only paper pulping like a kraft and sulfite technology, but the same is also for ethanol producers, because the lignin is also burned to produce energy. Okay. Let's look more closely what are industrial sources of lignin, what it could be and what they're doing it. You see, actually, we can say we have on market like 1 million ton per year the lignin. This is mostly lignosulfates. Maybe only 1% of it will produce the vanillin. I think Borregaard producing some 15,000 tons or something like this. All the other part coming from oil-based, and about 100 kilotons per year is the kraft lignin produced by Tomtar. Actually, I think they closed also Sunila in Finland. That's mean maybe this number is not correct anymore, even less. And all the other lignin suppliers like Soda Lignin, this is stopped actually, and Organosol are just very small amount of lignin on the market. But still, they're thinking about to have a very potential to grow. And it's predicted that kraft lignin has this market potential at least. But of course, kraft lignin has a limit because they have to recover the chemicals. That means you have to have like pulp mill which producing I think 1 million ton per year of cellulose. produce, you need about, I don't know, 6 million cubic meters of wood. That means basically in Estonia we can't have the kraft mill which can also recover some lignin, because we don't cut the trees so much. Which is it true or not? Okay. The sugar and bioethanol biorefinery concept, which actually believed to grow very soon, and if this will be realized, then these guys predicted, or they took this data somewhere, they predicted that volume could be like 200 and more than 200 million tons per year. That means it's like 2 orders of magnitude higher than the maximum level could be from the kraft lignin. And this is North America alone. That means the potential is quite high. But like I mentioned before, right now there are actually no wood-based ethanol producers, because this is competition with the other sources for the sugars is economically it's not reasonable. That's why it's very, very important for this kind of biorefineries to valorize the lignin. Okay. This is nice picture. This is actually the first one too. This is made from image crater, and then I put the burned lignin, and I think it was like kraft lignin or something like this. They had this picture, the horns like in the hell. Yeah, it's very nice. Okay. Okay, some introduction what Timo did already, but why we don't polarize it? It's coming out from there. This is glue to all the cellulose together. That means this is very, very special biopolymer. Consists a lot of aromatic rings and so on. But the properties of lignin is still make some limitations if you're using these techniques to recover the lignin. It's not soluble in water. It's very poorly soluble in common solvents. The polymer itself is very heterogeneous. That means it consists of different molecular weight, molecules of different molecular weight. There are different bondages and also functional groups are quite different. Now, if you think about the kraft or then sulfite technology, these lignins are completely different. You can't compare them, and you can't use them the same way. Okay. The same story is with biorefinery lignin, mostly because it's the purity, because it still consists a lot of hemicellulose and cellulose residues, proteins, and so on. That's why it's more clever to just burn it, to just polarize. But biorefinery concept is here. First, some kind of biomass treatment. It could be different. Fipronil in Estonia using extrusion, then steam explosion, and quite weak acid. That means they can hydrolyze C5 sugars. Hemicellulose is broken down. I think it was like 99% or even more. That means they can take out the sugars. Now you can use some enzymes to hydrolyze cellulose to have a glucose, which is soluble, and then the final product is so-called hydrolysis lignin. What is the difference if we compare with Kraft and other methods? The structure is quite native. It's actually the same like Timo showed with ionic liquids. There are no harsh chemicals. That's why the structure is not changing. Also, the conditions are not so harsh. But still, it can consist some impurities, which are not helping to valorize lignin in the downstream processes. Okay. But also for native lignin, the problems are similar, like all the lignins. And there are two typical strategies for lignin valorization. This is lignin to direct materials. The very simple things are working right now, and they are also in the market. The other one is lignin to chemicals via depolymerization. Okay, there are some positive and negative stuff in the both. If we using depolymerization, then we will have some aromatic compounds, aromatic rings from lignin, which actually are similar to what we can have, like petrochemicals. From lignin, usually, you will have the mixture, which is very, very hard to separate, and also the compounds. What you finally can get from there are bulk chemicals, which again competing with oil-based ones. If you have like toluene or phenols, you can make again polystyrene or something like this, which are actually quite cheap materials, and we have a lot of it. Now, if you're going to pack to lignin directly to some materials, first, of course, we used lignin as a filler in some plastics or in bitumen or whatsoever. It's quite typical in the plastics. We have a lot of fillers. It's quite normal to have 30 to 40% of different fillers. This is also okay, but these materials and also lignin are not very well valorized, and that means it's more interesting to go back to the lignin structure. Do you have a lignin structure as a backbone of the compound? Because this is coming from nature. This is something what we are not able to do with petrochemicals. That means we have some platform to maybe to make the new type of materials, which could be with same properties what we have from oil-based ones, but also could be the completely novel ones. Okay. Like I said, for all the technical lignins, they have the typical problems, the heterogeneity of molecular weights and so on, and also low purity. There are some purities coming also from they are in a hydrolysis lignin. That means it could be quite good and also clever if we can extract or fractionate lignin that we can lead control the properties. There are actually many methods which are used also right now in in-industry, like ultrafiltration, but actually it's not working quite well for the hydrolysis lignin because there are cellulose due and this is quite expensive. You can use ionic liquids, you can use diapathetic solvents and so on, but also depends of the price. But we have used or we developing some strategy to use organic water mixtures. We could have very narrow molecular weight distribution. We could also to control the reactivity, the reactive groups, and the physical properties too. This is actually a nice picture. And then we can derivatize to put some to react with something to change the property of lignin, and then to find the application or to design it for the application. Okay, what we have done with water organic solvents, these all are based from biomass, from lignocellulosic biomass, from the sugars. They can be produced. There are many of them, and actually they're working quite amazingly. These are cheap, and you can recover them, of course, but you can also produce them in biorefinery. Okay, there are just few examples. Ethanol, tetrahydrofuran, and 2-methyl-tetrahydrofuran. And you can see that the solubility is different, but the molecular fraction, what we can take out, are completely different. The reactivity is different, and also the subunits and so on. And if we have these fractions, then we can go forward and start to think about the materials to use these fractions. For example, what we can do with these unique fractions, for example, polyurethanes. Polyurethanes like to react with aliphatic hydroxyl groups, and that's mean this kind of molecules where you have this ones more. Also, when we're using this type of molecules, we can have like hydrophobic properties or hydrophilic properties, and so on. And for example, for polyurethanes, this is well known. Isolation foams or other foams would wear these boots, for example. This is polyurethane, and this is natural leather, but we can make maybe also artificial leather when we control the, okay, like this one, 100% of lignocellulosic artificial leather, please. Or the other one is quite simple. That means we can make the boots like how these are clogs in Netherlands, the wooden boots. Okay, lignin-based epoxy resins is the other one. The epichlorohydrin is reacting quite well with phenolic compounds, with phenolic hydroxyl groups. That means when we're controlling the number of these groups, we can make the epoxy-based resins. This we can make the, for example, epoxy boats with mixture with some, I don't know, cellulose, nanofibers, or something like this. That's mean the wooden boat. Okay, this was one example. The other example, what I like to show to you is linked with celluloses, nanomaterials, which actually are the most advanced biomaterials and also most expensive materials right now from biomass. There are many applications. The properties are very, very interesting, very useful. You can see the list of different applications here. But just currently, I think in the last few years, the interests are growing because they found that the lignin has a strong influence to properties of nanomaterials. What is also important to note, if you know how you make the nanocellulose right now in the industry, that means you need very, very, very pure cellulose. Basically, you can use Kraft process. You can make like dissolving cellulose, which means you already have a yield just 30, max 35% to bleach cellulose. 30% of a starting material. All the other parts we're going to burn. Now, if you're making the nanocellulose, you're losing even more. That means you will have maybe 20%, maybe less the yield. Do you have lignin inside? Do not take it out. It could be quite good. Okay, it's time. This biorefinery, you can have a microcrystalline cellulose. We're using ultrasonic technology. This is also applicable in the industry, and they're using it in different places. But the same time, when we have a lignin also inside, I give you something to see more. You can smell it. You can touch it. This is like cosmetics, sun cream or something. You don't have to find the sun because it's already very sunny. And it will give you color too. But actually, we have just a few % of lignin cellulose mixture. And we changed the structure with just few minutes. And cellulose is in nano size, less than 100 nanometers. And the properties are completely different. Now we're using in the cosmetics, the oil-based chemicals, but we can change it to put some cellulose in, but also the mixtures with lignin could be very interesting. That means we have a new type of materials. Okay, I think it's time to finish. This is like a final slide where we came up to use these technologies. This kind of materials are very good starting materials for different startups and so on. And this is different type of technologies we're using. There are also scale-up ultrasound system to make some nanomaterials, but also to use microorganisms or enzymes to change these properties of lignocellulose, the lignin, and so on. And this is like, let's say, our startup, what we did like 1 year ago or something to make artificial leather. Okay, Ilona, look like I have to finish now. Thank you very much.
Thank you. So now time for questions.
Thanks. Nice talk, Siim. Thank you.
Thank you.
From the point of view of circular economy, we have now had talks about lignin, lignin depolymerization, then gasification, and also you talked about lignin in two different aspects of depolymerization and using lignin directly as a fill-in material. So what do you think? What's the future of circular economy in of the lignocellulosic biomass? As lignin is naturally evolved a very specific biopolymer. It's like a glue. It's a difficult material to work. So in nature, usually the metabolism, we know it breaks polymers down to amino acids or 3 carbon, very small compounds, and then builds the new ones. So how a human designed circular economy cycle would work, what do you think? Would we stay and don't break down the lignin and build from there, or do we go down to the single carbon, for example, gasification like the LanzaTech process, that gasification of wood residues and then gas fermentation to produce ethanol or higher value chemicals and ethanol to aviation fuels and all these things. Will we go to low carbon, or shall we stop at the polymer step and then go?
It's not difficult to answer because I'm quite sure that we're going to both ways. If we're going to use the common plastics what we're using, then probably it's easier to go and depolymerize something to have the similar properties and so on. But same time, like you said, lignin is very cool glue, very good structure is already, but we can also add some like peptide bonds and to use it as a glue again, because actually you can use polyurethanes as a glue. This is tested and this is quite simple. That means it depends on money and how expensive will be to go depolymerization way, or to use for some specific use. Specific use is, I think, is also important. Right now, we don't use it as a oil, but we have a lot because we don't know how to use it. That means in the start, we can use this one to make very specific and also expensive materials.
Thank you. More questions? So thank you, Siim. And